Hello and welcome to Deep Learning with Pytorch Lesson 11. Today we're going to be going through Chapter 7, which we're going to be, in Chapter 6 we built neural networks to tell the temperature, to convert temperature from Fahrenheit to Celsius. In this one we're going to be telling birds from airplanes. The code here, there's only two, datasets and birds underscore airplanes. They don't go through the entire code in this chapter. The first thing they do is they bring up the CFAR 10 data set here, which is just 10 different things. This data set is not used as frequently anymore. I think there's a CFAR 1000, which has 1,000 different categories. So we have 10 different categories listed here. We're going to break that down to just two categories, airplanes and birds. So first we're going to download the data set. Let's just get into the code and get going with it. So kernel, restart and clear output. And let's run this one. So just normal stuff here, importing pyplot, importing numpy, importing torch. This one is the data set download here. So to download the CFAR 10, it can just pretty much automatically do it. And we're going to save it in this path here. So let's go ahead and download that data set. So I've already downloaded it, but if you haven't, it shouldn't take too long. It's not an extremely large data set. So now we're doing a for loop here. The figure size is 8 by 3. Number of classes equals 10. And we're scrolling through it here, I and range number of classes. So I is going to go from 0 to 10. Subplot 2 by 5. 1 plus I, x ticks, y ticks. And it just kind of scrolls through here and puts an example of each image there. Type, it just shows what type of file it is. Length, I think that's okay. Length will be the amount of images within the entire data set. So that's 50,000 images. Image, comma, label, CFAR 10, 99, and image, label, class names, label. So when we run this, we should get image 99. We should get a 1, and it's 1 is an automobile. So 0 is an airplane, 1 is an automobile. If we tried 98, we would probably get something different. We get a deer. And this is just the showing what it is. It's a PIL image, which is a file type. I believe that it's fully a pillow file type. But it's basically just an image file, 32 by 32, RGB. So let's now we're going to plot that image, and we do that by doing plt.mShow image and plt.show. We run that, and we see the deer. So it's tough to see that, isn't it? And that's because we, with machine learning or neural networks, we are minimizing pixels. You know, it's not for humans. We would increase the pixels because it's not that bad, but each pixel is being fed into a neural network, and if you have so many pixels, it will increase the amount of computation significantly just by going from 32 to 64. And this is good enough for a computer to figure out what it is, so it all works out. We'll go ahead and look at this. Now this is important. This is the transforms that we can apply to tensors, essentially, or images in this case. So center crop, color jitter, compose, all of these normalize. PIL to tensor. That's going to convert this to a tensor. We're going to use that in a little bit. And then once we convert it to a tensor, we can convert it back to PIL image or to tensor. By applying different transforms to this, it's good on the early end of the neural network, you can get more data. So what are they saying here? This is just saying actual data. It's got a length of 5. Get item gives you that item. Here's the picture we just brought up. I don't know if they actually talk about image transforming. Okay, well basically by rotating the image, by zooming in on the image, cropping the image, and doing different transforms to the image, we can get more data into our data set, and the neural network will be better if we do those things. So that's why we do them. So from Torch Vision, import transforms to Tensor, transforms to Tensor. So what are we? Okay, so this command is this command. That's what we're setting this command to this command. If we wanted to, we could just use this, copy and paste it, and put it right here, and it'll do the same thing. But we're going to take image t, which is our red car up here, and we're going to transform that to a tensor, and then look at the shape of it. Okay, now it's a tensor. It's a 3 by 32 by 32. 3 is for the RGB color channels. 32 by 32 is pixel size. Let's go ahead and run this. This line of code just transformed our entire data set. So tensor CFAR10 equals datasets, CFAR10 data path, train equals true, download equals false, transforms equals transforms to tensor. We just transformed every image in our data set to a tensor. Okay, let's go ahead and run this now. So image t, I don't know what this comma is here for, but yes, image t is a tensor. So now we can look at the shape of image t and the data type. It should be a 3 by 32 by 32, and it should be float. Yeah. Okay, 3 by 32 by 32 and a float 32. So that's the data type. Max and min. Okay, 0 to 1. Oh, why is that? I guess that's just the scale of it. The max is a 0, the min is a 0, and the max is a 1. I thought the color scale went from 0 to 255. So at some point we must have maybe converted that and normalized it. I'm not sure. Okay, well, anyway, now we're going to permute the tensor. And it still is able to plot it. But we just changed the axes around. So now it's a 32 by 32 by 3. It's still able to figure that out. Let's go ahead and do this. And this and this. So what we did here is we calculated the mean. So the whole scale is from 0 to 1 in each of the values. I mean, maybe we could just say, let's see here. Let's say A. Let's say print image. So these are all the values within that tensor. So we have red values, green values, and blue values, and they scale from 0 to 1. All right, so we're going to take the mean of all of these values in the red, green, and blue direction, and we're also going to take the standard deviation. So the average red value is 0.49. The average it's RGB, or average green value, is 0.48, and so on. And here we go with the standard deviation. So now we have a formula to normalize our matrix. And that's what this line of code is going to do here. We're going to normalize it. We're going to take our mean. So here's the means. Okay. And here is the standard deviation. We're going to put that there. So now we're going to transform it. C410. Oh, what we're doing here is just saying, hey, we can do all this as soon as we import it. So we're kind of doing it here manually, but here we're doing it right as we import it. So transform C410 equals that data set, and go ahead and transform that to a tensor for us, and go ahead and normalize that tensor. Okay, so we're good. We did that. Is this line of code the same exact thing? Yep, it is. Okay. And do you want to see what normalized data looks like? There you go. That's what normalized data looks like. I guess they explain what happened there. I don't really know. The renormalized red car we get in figure 7.5, this is because normalization has shifted the RGB levels outside the 0 to 1 range and changed the overall magnitudes of the channel. All of the data is still there, it's just that matplotlib renders it as black. We'll keep that in mind for the future. Okay, so when we normalize the data, just some of the values get into the straight black range. Okay, so that's all there is for data sets here. Now we're going to get into the actual code of distinguishing birds from airplanes. This is all pretty simple stuff. Here's the fully connected model. The output will be probabilities. Probability of a dog versus probability of a human. For us, it'll be probability of a bird versus probability of a plane, right? We're differentiating between birds and planes. We're going to put a few more tools in the toolbox here, such as softmax, which I'll explain it here when we get to it in the code. Here's another image, and I don't think there's too much. We'll talk about the NLL loss function, so we're going to get a few more loss functions. We'll be able to just build the full neural network like that. Here's the difference between cross entropy loss and mean squared error, which we were using mean squared error before. So a lot of important stuff in this chapter. So this might take a little bit to break it all down and go through it all. I know that they do get into, I looked at the code, and they do get into utilizing, what is the word for it? I have to scroll down. I can't remember the word for it right now. A convolutional neural network. We're not going to be getting into the convolutional neural networks. That's next chapter. So when we get to that part, maybe I'll just end it, or maybe I'll run it to show it to you, but I'm not going to explain the convolutional part beforehand. I think the next chapter gets into convolutional. Yeah, next chapter 8 is using convolutions to generalize. So let's go ahead and import this stuff. Let's name all of our class names. And now we're going to grab this stuff. We're going to normalize it. We already know our mean and our standard deviations here, so we can just normalize it and transform it to a tensor right off the bat. I believe, although we're transforming it to a tensor to feed it into a neural network, we will have to do that command here where we, the permutation command, to get it into this format. So I wonder if you could do that here. I'm pretty sure we probably could. So what have we done here? We're taking two things and doing the same thing twice. This is our CFAR10, and this is our CFAR10 underscore val. So that's probably going to be for our validation set. So let's go ahead and run that. It looks like it's the entire data set is our validation set, and the entire data set is also our training set. This will most likely be our training set. So maybe they'll make that smaller in a little bit. Now we're going to go label map. So this is indexing here. This is an example of indexing. We're going to apply this label map to our CFAR2 and our CFAR2 val. So our CFAR10 will become a CFAR2. So that's what we're doing here. We're saying for image label in CFAR10, if label is in the 0 or 2. So now we're only getting the planes, which is 0, and the birds, which is 2. Okay, so let's run that line of code. It's taking a minute there. I don't know if that should take so long. Okay, well there it goes. Now we're going to run this line of code, which is now we're making a neural network here. So we could double check this if we wanted to. Didn't we do that in this last set where we printed one of these images like this? Let's just take this line of code here, put it here, and we'll say CFAR2, and let's see what happens there. So we have 0 in an airplane. What about 100? Bird. What about 101? Bird. 102? Bird. 103. Lots of birds here. We'll probably get back to an airplane in a minute. There's an airplane. So that kind of proves that we are only dealing with the airplanes and the birds. So now let's go ahead and make the neural network. This is a very important step. In, out equals 2. So model equals in sequential, in linear. So we have an initial linear layer of 3072 followed by 512. This code is written a little strange. I think in the book it's actually written like this, so I would prefer it to be like that. Let's just put it like that, I guess. I don't know why they are doing that, and I don't know what this is here for. Right? The book doesn't have that silly one thing there. Probably should have done this before the video. I apologize. And that looks like it, right? Okay. So I like that better because we can actually see what's kind of going on here. And that should be it. Maybe I won't do that for all of them, but let's run that. And that worked. Okay, so it's easier to read it this way. I don't know why it was written that other strange way. It just looks like only that one was written that way, so that's good. 3,000 in, 512 out. Then our nonlinear activation function, tan hyperbolic. Then from that, we go to a 512. This 512 must be matching that 512. This is the output of the first layer. It must match the input of the second layer. And the output of the second layer, which is our final layer, must match what? It must match the amount of classes that we are sorting by. If we were doing the CFAR10, we would have a 10 here. But we're doing the CFAR2, which is airplanes and birds, so we have in, out equals 2. So this is a neural network. That's the entire neural network, written down so simply. All right, so now we're talking about softmax here. Softmax is what we're going to need to get these in the right format. Let's look at the math equations for those. They're written here quite well. So if for the CFAR2, it'll only be 2 values, so it will actually be exactly this equation. For the CFAR10, it will go all the way up to 10, so it'll be E to the x1 over e to the x1 plus e to the x2 plus e to the x3 all the way to e to the x10. And what this will do is each element will be between 0 and 1, and the sum of all of our elements will be equivalent to 1. So now we are taking it, and it satisfies the constraints on probability. Because if there was a 50% chance of it being a bird and a 51% chance of it being a there's a 50% chance of it being a bird and a 51% chance of it being an airplane, that doesn't work in the laws of statistics, right? It can only be 50-50. So we're normalizing our output to these constraints. I mean, it's written very simply here. Each element is between 0 and 1, and the sum of the elements equals 1. You can take whatever values you want and put them in x1 and x2, and that will happen. So that's a nice little mathematical property. That's why mathematicians are so good at helping us further develop these. So let's go ahead and run the softmax. We're defining softmax here, so that's fun. And now we're going to have a tensor of... So let's look at this code actually though. So this is torch to the exponent x divided by torch to the exponent x dot sum. So this line of code is equivalent to these formulas here. So that's pretty cool. Now we can return the softmax and we get a value of 0.09. Could we say dot sum? It's 1, right? And just so we're all clear about that, what if we put a 42 in here? Okay, and now we do sum. It's 1. What if we put a 1,900, that big number there? Well, it couldn't handle that, could it? But it will always be 1. I think we're just getting too high of a number there. But it is 1. If you did it, it would be 1. Something's going on there to where it can't be 1. But according to the formula, it will always be 1. 4, 5, 6. Oh, I need to put a 0.0 probably. So that's a data type issue. So put on this 0.0. No, that didn't work. Okay, well, I don't know why it's not coming back as 1, but this one will. It must just be too large of a value. Huh. Let's see what it looks like if it's... I guess this number is a NaN, which is not a number. It counts this as not a number. I'm not sure why. But in that throws it off. If it goes over like 104 maybe, it's not a number. I'll have to look into that. I don't know why that would not be a number. Okay. But this is the softmax. That's the way that formula works. All we need to know is that we're taking these values and we are putting them into a space where the sum of these numbers is going to equate to 0, and also each element will be between 1 and 0. Okay, so now we have, instead of defining this, which is defined right here, we can actually just call it softmax equals NN dot softmax. The module is embedded within the NN module. X equals torch tensor, and now we can do the softmax of X. It will automatically, oh no, we said here, dimension 1. So if we do it along the dimension 2 or 0, we'll get a different answer. But along dimension 1, we get this answer. So what dimension you do it along does matter. Dimension 0 gave us a 0.5. That's because it's doing it along this dimension, so it's 1 and 1, so you get 0.5, 0.5. If we change that to a 4, we'll get something different. Pretty neat, but they wanted it in the first dimension. So if you're dealing with the tensor of multiple dimensions, you have to be careful and thoughtful about which dimension you place the softmax upon. Now we're going to redefine our neural network. Same thing as before, 3,072 layers to 512. Then we apply our nonlinear activation function to the results of this layer. Then we run it through another layer, and then we perform the softmax at the end of that. Okay, so now let's plot one of our images. The image doesn't look too great. I think that's because we normalized our data already. That's fine. It looks like a bird though. Okay. So what are we doing here? What is this shape of image? Batch image underscore batch dot shape. We are unsqueezing. So unsqueezing Huh. 1 by 3072. So if we say B, what is 32 times 32? 1024 times 3. So what we did here is we squeezed this down into one. It's not a one-dimensional vector, but it's close to it. We took the 32 by 32 by 3 and put it all in one line here. So that's that. Let's look at this. If we model that, so we just fed this image batch, which is just one image. We're taking this specific image as well. CFAR2, 0, the very first image within the data set. And we're running that through our neural network. But we've done no training, right? So we're just going to get random values. And it looks like we're getting a negative 0.1 and a 0.4. So that's what it gets with just random values within our neural network. When we create this neural network, there are random biases and random weights associated with these layers. You have to train those to be the correct number to shape your data into the form that you want in the end. Let's go ahead and run this one. Okay, so here we're looking at the index of it. It's just a one-dimensional tensor, as we just said. Here's another tensor that we are specifically writing. And then we're saying class index equals torch tensor 0, 0, 1, 1, unsqueeze along the first dimension. I'm not sure what we're doing here, but maybe that'll come. Maybe that'll be. Maybe we'll figure it out in a minute. Okay, so now they want us to define what we already know, which is the mean squared error, out minus truth. Okay, so I guess what they're saying here is they're defining something that either gives it a 1 or a 0. So this one gets a 1 and this one gets a 1 because these numbers are greater. Okay, so this is an example of the output of our neural network. It says, hey, 0.6% chance airplane, 0.4% chance bird. And what this line of code is doing is just setting the higher value equal to 1 and the lower value equal to 0. So we have a clear winner and a clear definition of which class we are in. And now we're going to operate or apply possibly the mean squared error as our error function, which, as you remember, is the truth is here, right? The out minus the truth squared, and the sum of that, and that's our error. That's the mean squared error that we have from this. So this was our truth, right? And this was our, sorry, dang, which one's the truth? Truth scatter. Yeah, this is the truth. This is the truth, right here. And this is the out. So we're subtracting the out minus the truth, squaring that, and we're getting this, and summing it at the end, and getting this as our error function. So really, this is more important because this is the function that we're going to be using. So let's just look at that. That's the negative log likelihood function. Here it is. Now this one is just better than the mean squared error. It's what people use when we're dealing with classification. If you're dealing with a classification problem, you're going to use the negative log likelihood function to do it. And now this is talking about the steps here. Let's just continue on. We'll define the likelihood here, but now the negative log likelihood of that. It's just another math function, okay? And rather than learn the function, sometimes it's just good to look at this graph and realize, like, that's what it is. So you get penalized heavily for being near 0, and you don't get penalized heavily for being near 1. I mean, that makes sense, right? If you want your classification to be 1, it's an airplane, you want it to be 1, it's not getting any error here, it gets a lot of error here. So not a very complex thing. It's a logarithm which logarithm function which helps to graph that. It's not just the logarithm, there's other stuff in it. But it's not always necessary to memorize these mathematical equations. Just know what the graph looks like, or don't. I mean, you don't really even need to do that. But it probably would help to do that. So now we're cloning some stuff. We're comparing in an NLL comparison. So the mean squared error, it's just penalizing too heavily, it looks like, whereas the NLL is not doing that. The NLL is better for classification. We're doing a softmax here. Let's just get to the neural network stuff. Okay, we're taking the log of the softmax. I think they're just trying to show how you, perhaps this is in fact the NLL. But let's look at this layer. Okay, so finally we are here. We're going to run the neural network now. And this is good. This is the first neural network we're going to run. We have 3,512, outputs 2, learning rate e to the negative 2, number of epochs 100, and we have that. This is just defining the neural network, if you remember, and we'll wait for that to get finished up. We're using stochastic gradient descent as well on this one. There's a chance that this line of code might not work, because I think it didn't work before when I looked at this. Which I'm not sure why that wouldn't work. This is not a complicated neural network whatsoever. It's very simple. I know that in the book they say it doesn't get great results. Oh, okay, here we go. Oh, so darn. I should probably run this, and I guess we'll have to end the video here and my next video will be on the results of this. It looks like it's just taking a while to run. We're going to be doing 100 epochs. One has just been loaded up. So I'll run this entire code and look through it and give a good video to finish up chapter 7. Okay, thank you for watching.